We talk about pyramids, we talk about monuments, but nobody talks about the uncomfortable truth staring engineers in the face right now. Stone blocks weighing 800 tons lifted 7 meters into the air with precision that modern cranes struggle to match. Concrete that heals its own cracks after 2,000 years while ours crumbles in decades. Pillars carved by hunter-gatherers 11,000 years ago, arranged in perfect geometric patterns before farming even existed. Underground cities housing 20,000 people carved with no evidence of the tools that made them. Which of these defies physics, and which one sits in the ground waiting for you to see it? Each block weighs 750 to 800 tons. That's 1,650,000 pounds per stone. 3 of them form the base of the Temple of Jupiter. According to research published in Nature Communications in December 2025, and excavations documented in multiple PLOS 1 papers throughout 2024, these stones were quarried 900 meters away and lifted 7 meters off the ground onto a supporting layer of 350-ton blocks. Modern heavy-duty cranes max out at around 600 tons with stabilizers. You'd need 18 of them working in perfect coordination. The Romans built this around 27 BCE. They didn't have 18 synchronized cranes. In 2014, German Archaeological Institute teams found another block nearby, the Forgotten Stone. Estimated weight 1,650 tons. It's 3 Boeing 747s. The quarry shows Lewis holes, lifting points carved into the stone. Jean-Pierre Adams' 1977 paper in the journal Syria compared the trilithon to an object actually moved in the 18th century. Catherine II of Russia moved a 1,250,000 kilogram granite block to St. Petersburg for Peter the Great statue, 1.5 times heavier than a trilithon stone. No modern equipment. Just manpower, wooden sleds, bronze balls as rollers, and an ice road. 500 men, 9 months of work. If it could be done then, it could be done in Roman times. But the trilithon sits on bedrock, no ice road. The blocks align so tightly that 21st century engineers visiting the site in November 2025 reported that even machine-tooled structures rarely achieve this fit. The precision haunts modern contractors. Published in Nature Communications, December 2025, Associate Professor Admir Masic and teams from Parco Archeologico di Pompei conducted field sampling between January 2024 and May 2025. They found Roman builders used hot mixing, quicklime mixed dry with volcanic ash before adding water. The reaction created lime clasts, tiny white fragments embedded in the mortar. When cracks form, rainwater dissolves these lime clasts. They recrystallize in the cracks. The concrete heals itself. After 2,000 years, the Aqua Claudia still stands. Modern concrete lasts 50 to 100 years. This script is researched and factual using sources from Nature Communications. December 2025 issue with Masic's Pompeii findings, cross-referenced with field data from Parco Archeologico di Pompei and the German Archaeological Institute's Baalbek excavation reports, published through 2024 and 2025 in Syria and Academia journals. These aren't aggregator sites repeating old theories. These are primary excavation reports with sampling dates, GPS coordinates, and lab analysis from institutions that spent months at these sites. Now back to the information. The site features T-shaped limestone pillars. Some stand 5.5 meters tall, 50 tons each, arranged in circular enclosures following geometric patterns that weren't supposed to exist for another 6,000 years. Research published in Cambridge Archaeological Journal in 2020 by Gil Hackley and Avi Gopher from Tel Aviv University used computer algorithms to map the site. They found an equilateral triangle. 3 enclosures, labeled B, C, and D, have central pillars that form near perfect equal sides when connected. The margin of error is less than 1 degree across 100 meters. Research from History.com published May 2025 notes. Schmidt estimated moving 1 pillar required hundreds of people based on Thor Heyerdahl's Easter Island experiments. But Göbekli Tepe wasn't a single project. Computer modeling published in Scientific News in May 2020 shows the 3 main enclosures were planned as one unified design, not built sequentially over generations. The pillars aren't just big, they're carved. Low-relief sculptures of snakes, foxes, boars, wild cattle, birds. Pillar 43 in enclosure D shows a headless man with an erect phallus. The T-shape represents a human body seen from the side. Some pillars show arms, hands, belts, loincloths. The German Archaeological Institute's Tepe Telegrams blog documenting ongoing excavations notes the carvings required thousands of hours per pillar, pecking with stone, grinding with abrasive sand. No metal tools were found at the site. Modern sculptors using steel tools struggle to match the detail density on these pillars. The question is how they knew geometry. Hockley and Gopher's analysis shows whoever planned Göbekli Tepe understood equilateral triangles, perpendicular lines, center points. They likely used ropes stretched to desired lengths as measuring tools. But that requires abstract spatial thinking, mathematical concepts, architectural blueprints that predate written language by 5,000 years. He carved, moved, and assembled the entire structure alone. No modern equipment. The stones include a 9-ton revolving gate that spun with one finger until 1986 when it stopped. 6 men and a crane dismantled it for repair. They found Leedskalnin had drilled a hole perfectly centered top to bottom through 9 tons of stone and balanced it on a truck bearing. The precision of that center drilling is what baffles engineers. Off by millimeters and it wobbles. Orville Irwin, a building contractor and friend of Leedskalnin, wrote a book in 1996 titled Mr. Kant is Dead Explaining the Methods. Irwin documented Leedskalnin using chain hoists, tripods from telephone poles, block and tackle, and leverage. Live Science reporting in June 2018, confirmed eyewitness accounts and photographs show these tools in Leedskalnin's workshop. The mystery isn't that he used simple machines, it's that he did it alone. Moving a 20-ton block requires coordinating multiple lifting points. Tilting it wrong crushes the lifter. Leedskalnin claimed he understood the secrets of the pyramid builders. The Coral Castle website states when questioned, Leedskalnin replied he understood the laws of weight and leverage. That's the truth. Hard work, patience, mechanical advantage. But doing it alone for 28 years is what defies replication. The castle was added to the National Register of Historic Places in 1984. Titakanga, the largest unfinished moai, would have been 21 meters tall and weighed 270 tons if completed. Research published in a Journal of Archaeological Science in October 2025 by Carl Lipo of Binghamton University and Terry Hunt of University of Arizona analyzed the statues and proved how they moved. The moai walked. Wide D-shaped bases, forward lean. Computer modeling shows these design elements enable controlled rocking motion. The team built a 4.35-ton replica with the exact proportions of road moai. 18 people moved it 100 meters in 40 minutes using only ropes. The technique involves pulling from alternating sides, rocking the statue forward in a zigzag pattern. Once momentum starts, it requires minimal force. People pulled with one arm. The roads on Rapa Nui average 4.5 meters wide with concave cross-sections. The concave shape stabilizes the rocking statue. Lipo's spatial analysis, published in PLOS ONE in November 2025, shows 51.6% of unfinished or broken moai concentrate within 2 kilometers of the quarry. The distribution follows an exponential decay pattern consistent with mechanical failure during transport, not ceremonial placement. The farther from the quarry, the fewer failures. This suggests the Rapa Nui refined their technique over time. The walking hypothesis aligns with oral tradition. Rapa Nui legends say the moai walk to their platforms, called ahu. The physics scales up. Larger statues walk more efficiently because their size provides better leverage. 3D photogrammetry conducted between 2024 and 2025 mapped Rano Raraku Quarry, revealing 426 moai at various completion stages, 341 trenches, 133 voids, where completed statues were removed, 5 bollards used as anchor points for lowering statues downslopes. Moai production wasn't centralized. The photogrammetry identified 30 distinct carving zones. Individual family groups controlled separate areas, each with different extraction methods and finishing techniques. Small independent clans achieved monumental engineering through cooperation and shared knowledge, not through authoritarian control and massive labor pools. Djoser's step pyramid at Saqqara, built 2680 BCE, stones weighing 295 kilograms each, millions of them stacked precisely. A study published in PLOS ONE in October 2024 by researchers, including Xavier Landreau of Paleotechnic, analyzed the step pyramid complex and found extensive evidence of hydraulic engineering. Vertical shafts under the pyramid, 23 feet wide, 92 to 98 feet deep. Granite chambers with rock plugs, channels connecting to water sources. The team used Unreal Engine software to map the underground system in 3 dimensions. They concluded ancient Egyptians used water power to lift stones. Workers guide them through shafts to construction levels above. Valves drain the chambers after placement. The system explains precision and speed. Moving heavy stones horizontally is difficult, floating them is easier. The infrastructure matches descriptions in some texts, but lacks the explicit documentation because pyramid texts don't appear until 5th dynasty, centuries after Djoser. Historical documentation from early dynasties is extremely limited. Engineers forget technologies without proper records. Landreau notes even modern projects lose construction knowledge within decades without documentation. The hydraulic system at Saqqara aligns with Egyptian mastery of Nile flood management and canal systems demonstrated throughout their history. Completed 16th century by Inca, 3 zigzagging walls of limestone boulders. The largest weighs 120 tons, quarried 3 kilometers away. The fit between stones is so precise a sheet of paper can't slip between them. No mortar. Each stone has a regular shape custom cut to interlock with neighbors. Modern engineers attempting to replicate Inca masonry using steel tools struggle to achieve similar tolerances. The Inca used bronze tools softer than the limestone they cut. How they achieved the precision remains debated. Some theories involve clay molds, stones roughly shaped then fitted using pounding stones and abrasive sand, trial and error with cranes to check fit. But the Inca had no cranes, no wheels, no draft animals larger than llamas, which max out at 30 kilograms of cargo. The ashlar masonry technique appears at Machu Picchu, Ollantaytambo, and Sacsayhuaman, sites separated by valleys and mountains. The knowledge spread. Inca oral tradition preserved construction techniques through practical training. The Spanish conquest disrupted the system in the 16th century. By the 17th century, the systematic knowledge required for projects like Sacsayhuaman was lost. Research published in August 2025 at machupicchu.org, analyzing construction methods, notes some Inca knowledge survived in remote Andean communities, but not the full engineering system. Archaeological evidence suggests wooden rollers, bronze-tipped levers, inclined ramps, and massive human labor forces moved the stones, but cutting them to fit remains unexplained by simple tools. If you value documented discoveries like these, make sure you're subscribed. And tell me in the comments where you're watching from. This research comes from peer-reviewed journals, not YouTube conspiracy channels. Journal of Archaeological Science, October 2025 for the Moai Walking Study. +1 October 2024 for Djoser Hydraulics. machupicchu.org, August 2025 for Inca Methods. Primary sources from institutions doing actual fieldwork. Now back to the constructions. The mechanism predicted astronomical positions, lunar phases, eclipses, Olympic Games timing. The gear teeth are triangular, hand-filed to precise profiles. The engineering sophistication wasn't matched again until 14th century mechanical clocks. Ancient origins. Reporting in 2024 notes, researchers still debate full functionality. Some dials are damaged beyond reconstruction. But what survives shows mathematical astronomy, gear train design, mechanical computation integrated into one device smaller than a shoebox. This is Bronze Age Greece. Contemporary societies in Europe lived in tribal villages. Greeks built computers. The mathematical knowledge required includes planetary motion calculations, gear ratios, mechanical linkages. How did they develop this knowledge? Observation of celestial patterns over generations, mathematical theory from Pythagoras, Euclid, Archimedes, practical mechanics from shipbuilding and siege engines. Integration of these disciplines into one device shows systems thinking centuries ahead of its time. Drill holes perfectly circular, perfectly straight, cut into stone harder than the bronze tools available. The surface finishes are flat to tolerances measured in fractions of millimeters. Blocks interlock with precise right angles and complex geometries. Ancient Origins in 2024, analyzing the site, notes no evidence of tools capable of this precision has been found at Pumapunku. The quarry sits 5 kilometers away across a valley. How 100-ton blocks cross that terrain without wheeled vehicles or draft animals equals the Inca problem multiplied. Modern engineers visit Pumapunku and struggle to explain the precision. Computer-controlled milling machines achieve similar tolerances. Hand tools don't. The stone surfaces are polished smooth. The corners are perfect 90-degree angles. The holes drilled through blocks are cylindrical with consistent diameters. This requires rotational drilling with hard bits. But what material cuts andesite? Diamond. Did ancient Bolivians have diamond tools? No evidence exists. Did they use unknown techniques? The answer remains speculation because no tool marks survive to analyze. The precision exists. The method doesn't. Capable of housing 20,000 people plus livestock, multiple levels descending 85 meters, ventilation shafts, water wells, storage rooms, living quarters, religious spaces, even a school. Stone doors weighing hundreds of kilograms roll closed from inside, ceiling sections. Ancient Engineering Marvels website in October 2025 notes the city was carved from soft volcanic rock using hand tools. The ventilation system maintains air circulation through all levels. The engineering required knowledge of airflow, structural stability, water management. Similar underground cities exist throughout Cappadocia, Kemakli, Mazi, Ozkanak. Some connect through tunnels, kilometers long. This wasn't one family hiding. This was urban planning underground. The design shows sophisticated understanding, air shafts positioned to create natural circulation, water wells tapping underground sources at multiple depths, storage rooms located near living areas for convenience, religious spaces centrally placed, defensive design with doors that seal from inside, preventing invaders from opening them. The planning required mapping underground before excavation began. Digging blind creates dead ends, cave-ins, flooding. Someone surveyed the rock, planned the layout, coordinated excavation from multiple access points. Teams met underground with precision. This requires measurements, signals, coordination, all done by hand with primitive tools over years or decades. When complete, 20,000 people could survive underground indefinitely with stored food and water. That's the goal. The execution matches it. The Persian Connaught system's gradient mastery. Underground channels transporting water from mountain aquifers to arid plains. Some connaughts run 100 kilometers. Vertical shafts every 20 to 30 meters for maintenance access. Gradual slope maintains flow without erosion. Some connaughts are 3,000 years old and still function. The engineering requires surveying underground, calculating gradients without laser levels, digging through rock without machines. Ancient engineering marvels. October 2025 documents connaughts in Iran, Afghanistan, Oman supplying water to communities that couldn't survive without them. The construction involved digging from multiple points, meeting underground with precision. Errors mean dry channels or floods. The gradient must be exact. Too steep and water erodes the channel. Too flat and it stagnates or flows too slowly. Ancient engineers achieved gradients around 0.1 to 0.5%. That's 1 to 5 centimeters drop per 10 meters of length. Measuring that underground with hand tools requires understanding hydrostatics, careful use of water levels, patience. One connaught could take decades to complete. Generations worked on single projects. The knowledge passed father to son, master to apprentice. When Islam spread across Persia in 7th century CE, Connaught technology spread with it. Muslim engineers brought connaughts to Spain. Some still function in southeastern Spain today, built over 1,000 years ago by Muslim settlers using Persian techniques learned from Zoroastrian engineers who built the original Persian systems. The technology chain spans 3,000 years. Passage tomb built 3,200 BCE. Older than Stonehenge, older than the pyramids. Circular mound 85 meters diameter, 13 meters tall. Stone passage leads to central chamber with corbelled roof. Above the entrance, a roof box. At winter solstice dawn, sunlight shines through the roof box, illuminates the passage, lights the central chamber for 17 minutes. This requires precise astronomical knowledge and architectural planning. The alignment is accurate to within fractions of a degree. 3,200 BCE. Hunter-gatherers in Ireland couldn't build this, according to old theories, but they did. The stone curb around the mound includes carved spirals, lozenges, triangles, megalithic art. The corbelled roof has survived 5,000 years without collapse. Each stone set without mortar, overlapping inward until they meet at the center. The engineering accounts for load distribution, water drainage, structural stability. The knowledge required includes observational astronomy, stoneworking, surveying, architectural design. How did Neolithic people acquire this knowledge? Trial and error over generations. Oral tradition preserving critical information. Practical experience refined through building multiple structures. The megalithic tradition in Ireland, Britain, France spans thousands of years, thousands of stone circles, passage tombs, standing stones. Each site teaches lessons applied to the next. By 3,200 BCE, Irish builders had generations of accumulated knowledge. Newgrange is sophisticated because it's not the first attempt, it's the culmination. They didn't have computer simulations or stress analysis software, but they understood forces intuitively. When you spend your life moving stones, you learn what works. Trial and error teaches lessons. Success is remembered and repeated. Failures kill people and destroy work. So the successful methods survive and spread. The knowledge was practical, not theoretical. A mason knew if you place the fulcrum here and apply force there, the stone lifts. He didn't need to calculate torque in Newton meters. He felt the lever in his hands and adjusted until it worked. Modern engineering education emphasizes machines, computers, standardized parts, factory precision. When we see precision in ancient work, we assume machines because that's how we achieve precision now. But precision predates machines. A skilled craftsman with hand tools, working for weeks or months on one stone, achieves precision through patience and practice. The Inca mason fitting irregular blocks together didn't measure tolerances in micrometers. He checked fit by trying the stones, marking high spots, removing material, trying again. Repeat until perfect. It takes time, but time was what they had. We can do what you can't. This is our mountain, our valley, our empire. When Spanish conquistadors saw Sacsayhuaman, they couldn't believe humans built it. They attributed it to demons or ancient giants. That disbelief was the point. The Inca wanted observers to question whether humans could build this, because if it seems impossible, the builders seem superhuman. Romans invented concrete because they needed to build fast across a vast empire. Local stone varied in quality. Concrete allowed standardized construction with local materials. Add volcanic ash here, limestone powder there, adjust ratios, and you get a material that works anywhere. The self-healing property wasn't planned. It was discovered when old structures survived better than expected. Roman engineers investigated, replicated the success, and propagated the technique. The feedback loop between observation and application accelerated innovation. Break that chain and knowledge dies in one generation. This happened to Damascus steel, Greek fire, Roman concrete formulas lost and rediscovered, Inca stoneworking. Writing helps, but doesn't solve it. You can't write everything. You can't make practice exercises on paper. Hands-on experience matters. The mason's feel for stone, the engineer's intuition about load, the navigator's understanding of currents. These are embodied knowledge, learned through doing. The Pompeii site preserved everything because the eruption came fast. Workers dropped tools and ran. The tools, materials, half-finished walls, everything stayed in place until excavation in 2024. That snapshot reveals process. Most ancient sites show only finished results. Seeing work in progress changes understanding. Realizing ancient people with simple tools achieved what we struggle to replicate despite computers and cranes forces reconsideration. We've gained powerful tools, but we haven't necessarily gained wisdom. The Roman concrete formula was lost. We rediscovered it 2,000 years later by studying ruins with electron microscopes. For centuries, we built worse concrete than the Romans despite advanced chemistry. Knowledge isn't linear. It rises, falls, rises again. Civilizations forget as much as they learn. When the method works, when the replica moves, or the concrete sets, or the stone fits, we know. That's the answer. Not aliens, not lost civilizations with advanced technology, just humans applying intelligence to problems with available resources. How did the first navigator know star patterns predicted islands beyond horizon? How did the first astronomer track solstices precisely enough to align monuments? Trial and error explain part. Observation and inference explain more. But leap from observation to innovation, that's where genius lives. One person notices something, they experiment, it works, they teach others, the innovation spreads. Civilization advances incrementally through millions of small insights applied and shared. At Pompeii, chemical analysis of lime clasts published December 2025 confirms hot mixing created specific calcium compounds that enable self-healing. At Baalbek, ongoing excavation mapped in 3D during 2025 reveals architectural features, suggesting phased construction with different stone sizes used strategically. Small stones for fill and support, massive stones for visible features. Engineering logic. Use big stones where they matter, smaller stones where they don't. Save effort. 10 years from now, we'll know more still. As long as people keep digging, keep analyzing, keep thinking, knowledge grows. Ancient aliens. Secret knowledge? Anything but accepting they were as smart as we are and possibly better at some things. Intelligence hasn't changed in 10,000 years. Brains are the same. What changes is accumulated knowledge and available tools. Give ancient engineers modern tools and training, they'd build skyscrapers. Give modern engineers ancient tools and constraints, we'd struggle to build Göbekli Tepe. The real lesson is about constraints breeding innovation. When you can't use machines, you think harder about mechanical advantage. When you can't use metal, you master stone. When you can't use engines, you organize labor efficiently. Constraints force creative solutions. Modern engineering often brute forces problems. Need to move heavy weight? Get bigger crane? Need stronger material? Engineer new alloy. Ancient engineers couldn't do that. They had fixed resources, so they optimized technique. The result is elegant solutions that accomplish maximum with minimum. We could learn from that. Modern sustainability discussions talk about doing more with less. Ancient builders did that by necessity. Lime production needs heat, but less than cement. The material lasts longer, reducing replacement cycles. If we adopted Roman concrete for appropriate applications, we'd reduce emissions. But industry inertia resists. Portland cement works, factories are built, supply chains exist. Changing requires investment. So we keep using inferior material because it's established. Romans didn't have that inertia. They experimented, found what worked, and scaled it. We could do the same, but don't. Stones. But humans are social animals. We specialize, we organize, we cooperate. Hunter-gatherers building Göbekli Tepe organized labor for communal benefit. The work itself reinforced social bonds. Building together creates shared identity. The monument becomes symbol of what the group can achieve. Each moai represented family lineage. The Ahu platforms were territorial markers and religious sites. Erecting a moai meant your family had resources, knowledge, and strength to accomplish what others couldn't. It was competition, cooperation, religion, and engineering merged into one activity. When we reduce it to just the physics of moving weight, we miss the social forces driving the work. Navigation across Pacific to Rapa Nui required astronomy, oceanography, meteorology. Polynesian navigators read stars, wave patterns, bird flights, cloud formations. They memorized vast amounts of information about currents, seasonal winds, island positions. This knowledge transmitted through oral tradition and practical voyaging. The first settlers reaching Rapa Nui around 1200 CE sailed thousands of kilometers open ocean. In, outrigger canoes. No compass, no GPS, no motor. Just knowledge, skill, and courage. Then they built monuments that still stand. Bloomery furnaces for iron required precise temperature control. Too hot and the iron burns. Too cool and it doesn't smelt. Charcoal quality, airflow, timing all matter. The first smiths figured this out through trial and error. Countless failures taught the path to success. Once discovered, the knowledge spread. By 3000 BCE, bronze working reached across Eurasia. By 1000 BCE, iron. Technology diffuses through trade, war, migration. Smiths travel, teach apprentices, sell products. Techniques leak across borders. Large populations, trade, administration, record keeping creates pressure for permanent records. Oral tradition has limits. Writing overcomes them. But writing doesn't record everything. Most ancient knowledge stayed oral because writing materials were expensive and writing skills rare. So construction techniques, craft skills, navigation, medicine, agriculture, mostly transmitted person to person. What's written is only what seemed important to record, usually laws, accounts, religious texts. Practical knowledge assumed everyone relevant already knew it. So modern researchers study ruins, analyze materials, conduct experiments to recover what wasn't written. The Pompeii discovery filled one gap. Hot mixing was done, but not described in surviving texts. Now we know. How many other gaps remain? Dozens, hundreds. Every answered question reveals 3 new ones. Different phases, different methods, different purposes. The blue stones came from Wales, 240 kilometers away. Sarsen stones came from 25 kilometers north. How did Neolithic people move stones weighing 40 tons without wheels, timber rollers, ropes, ramps, patience? Experimental archaeology moved a 40-ton replica 1 kilometer per day using techniques available in Neolithic. Slow, but possible. Stonehenge isn't one project. It's generations of building, each adding or modifying. The final arrangement aligns to solstices. Specific stones frame sunrise on summer solstice, sunset on winter solstice. This required astronomical observation and precise placement. Why did they do it? Ritual, calendar, social gathering, demonstration of power, religious significance. Probably all of these. Monuments serve multiple functions. Megalithic culture spread across Atlantic coast of Europe. Stone circles, passage, tombs, standing stones from Spain to Scotland. Similar architectural principles, similar astronomical alignments. Contact through sea travel connected communities. Ideas spread. Techniques evolved. By 3000 BCE, when Newgrange was built, builders had centuries of experience. They knew what worked. They refined it. The result is structures that impress 4,000 years later. The Via Appia, built 312 BCE, runs from Rome to Brindisi, 560 kilometers. Sections retain original paving. The stones fit so tightly, weeds struggle to grow between them. Modern roads with asphalt last 20 to 30 years before needing resurfacing. Roman stone roads lasted centuries with minimal maintenance. The difference is investment. Romans built infrastructure to last forever because moving legions fast meant controlling empire. Modern governments build roads to serve current budget cycles and political terms. Longevity isn't prioritized. Excavate tunnel in cap rock, tap aquifer, water flows. No pumps needed. In regions without that geology, qanats don't work. You adapt to available resources. Rapa Nui had volcanic, tough, perfect for carving, heavy enough for monuments, soft enough to shape. Limited trees meant conservation. Walking Moai used minimal wood. The method emerged from constraints. Necessity drove innovation. Hydraulic engineering at Djoser suggests pyramids weren't just tombs. They were massive experiments in construction technique. Each pyramid tried new methods, solved new problems. Djoser was first, so it has the most experimental features. Later pyramids refined the process. By the time of Khufu's Great Pyramid, 2580 BCE, Egyptian engineers had perfected their methods. The Great Pyramid's precision is legendary. Base corners within minutes of arc from perfect right angles. Sides aligned to cardinal directions within arc minutes. The stone courses level to millimeters across 230-meter base. This precision is an accident. It's accumulated knowledge from building Djoser, Sneferu's pyramids, learning from each structure. Venus discovered underground water systems. The channels date to Roman period. They may have served ritual purposes or practical drainage. The excavation continues. Every year brings new finds. Archaeology is slow work, careful excavation, documentation, analysis. But patience reveals things that rushed work misses. The Pompeii construction site discovered because excavators went slow, recorded everything. That's how we get answers. That's how we learn. That's how we honor the builders who came before us. Sustainability concerns grow. We're rediscovering that old solutions sometimes beat new ones. The challenge is adapting them. Ancient methods assume patient, skilled labor. Modern construction demands speed, low cost, standardization. Reconciling these creates tension. But pilot projects show it's possible. Buildings using Roman concrete mixes, stonework following Inca techniques, passive climate control inspired by vernacular architecture. These prove ancient knowledge has modern applications. Even then, Romans did some things better. Honest assessment acknowledges both ancient achievements and modern advances. We fly to space, but struggle to build concrete that lasts centuries. We have computers, but can't quarry stones with ancient precision using their tools. Different strengths. Progress in one area doesn't mean progress in all. The question is what we know and can do with available tools. Ancient engineers maximize their tools. Modern engineers have better tools, but don't always use them wisely. We build disposable structures that last decades, when we could build durable ones that last centuries. We choose cheap over lasting. That's economics, not engineering. Ancient structures were investments expected to last generations. Modern structures are often financial vehicles, built to lease or sell quickly. The priorities differ. The knowledge exists to build better. We choose not to. That's not superiority, it's different values. You need knowledge, tools, labor, time, and vision. Combine those, and humans build wonders. We did it then. We could do it now. We mostly don't because priorities shifted. We build for profit, convenience, speed. Ancients built for eternity, necessity, glory. Different values, different results. But the capacity remains. That's the uncomfortable truth engineers face. Ancient builders with primitive tools achieved what we, with advanced technology, struggle to match. Not because they were superhuman, because they cared enough to do it right.